One empty space isn't actually empty. What we usually imagine as nothing is, according to quantum physics, full of activity. In so-called empty space, tiny particles constantly pop into existence and disappear again almost instantly. These are called virtual particles. They briefly borrow energy from the universe and then vanish, but their effects are real and measurable. One example is the Casimir effect, where two metal plates placed very close together in a vacuum slowly pull toward each other, not because of gravity, but because of quantum activity in empty space. This means that even the quietest, emptiest parts of the universe are never truly still. Two particles can stay connected no matter how far apart they are. When two particles become quantum entangled, they stop behaving like separate objects. Instead, they act as parts of a single system, even if they are separated by enormous distances. If you measure one particle, the other instantly takes on a matching state. Nothing travels between them, no signal, no energy, no information moving through space. Albert Einstein famously disliked this idea and called it spooky action at a distance. Experiments have repeatedly confirmed that this strange connection is real, suggesting that, at a fundamental level, the universe may not be locally separated the way we experience it. 3. Particles don't have definite properties until they are measured. In the quantum world, particles don't exist as tiny solid dots in one specific place. Instead, they exist as probability waves, spread out over many possible locations and states at once. When a measurement or interaction occurs, the particle suddenly chooses a single outcome. This is known as the observer effect, but it doesn't mean human consciousness changes reality. It means physical interaction does. Before measurement, reality exists as a range of possibilities. After measurement, only one becomes real. At the deepest level, the universe seems to run on probabilities rather than certainties. 4. At very small scales, time can move backward. Most of our everyday experience assumes time only moves forward, but quantum physics doesn't always care about direction. Some particle interactions follow equations that work just as well if time runs backward. In certain experiments, particle behavior looks identical whether time is moving forward or in reverse. This doesn't mean you can rewind everyday events like breaking a glass, but it does suggest that the arrow of time may not be a fundamental law. Instead, time flowing forward may emerge from large, complex systems, like thermodynamics, rather than from the basic rules of the universe itself. 5. You never actually touch anything. When you place your hand on a table, it feels solid, but on the atomic level, your atoms never make direct contact with the table's atoms. What you feel is electromagnetic repulsion. The electrons in your atoms repel the electrons in the table's atoms, creating the sensation of solidity. Since atoms are mostly empty space, all physical contact is really the interaction of invisible forces. In a very real sense, everything you touch is something you're being pushed away from. 6. The universe is fundamentally random, but still predictable. Individual quantum events are completely unpredictable. There's no way to know exactly when a radioactive atom will decay or precisely where a quantum particle will appear. However, when you observe huge numbers of particles, clear and extremely accurate patterns emerge. While single events are random, the overall behavior of many particles follows precise mathematical rules. This means the universe is chaotic at the smallest scales, yet remarkably orderly when viewed as a whole, randomness and predictability existing at the same time.